we discussed about the properties of rings as well as ideals, and I just started describing the ring homomorphism. So while describing ring homomorphism, I first initially started with a few interesting properties of homomorphism of groups, and to make it understand, I started with few examples. And I mentioned that these examples, for example, I started with few groups like Q quotient Z. I then started with say R quotient Z, and then C quotient Z. And also I had few groups like the groups like all such complex numbers Z belongs to C star. So that C star means C minus 0, means all non-zero complex number such that Z to the power n equal to 1, where this n varies. N belongs to natural number union 0. That means if I drop this part, then that will give me nth root of unity. But here this n varies. So for n equal to 0, it means 1. For you can drop this even. Okay. So for n equal to 1, you have all such z. So you can drop this. Okay. Also z such that z to the power 1 equal to 1. That means it's 1 basically. Then you have all such z square equal to 1. That means all square root of unity and so on, cube root of unity and so on. So this is basically an infinite set. Again, I may have S1. That means all such z belongs to C star such that mod z equal to 1. Geometrically in the complex plane, you will have a circle. So if we draw it on the complex plane, then that will represent a circle with center at 0, 0. Okay. So all this radius will be 1. So this is nothing but unit circle. So you can understand that this is a subset of C star. Okay. And maybe another. So if I write it 1, 2, 3, 4, 5, and as 6, if I write C star with respect to dot. So all of them, they form groups. Okay. Now the question is, I am telling you that there is a pairwise, like you can pair. For example, say suppose I am pairing 1 and 4. Then I am saying that 1 and 4 are isomorphic. So they are group isomorphic. That means there must be some group isomorphism between these two uh, groups. So you may not see very quickly. It requires little bit of properties of complex analysis and all to see all those things. But they are all kind of geometrical things. So you can see that they are all geometrical things, and this is so they are very much related, and these groups and are very important from competitive exams viewpoint, because in many of the question papers of NET, GATE, or even NBHM, or even the TIFR exams, you will be asked questions from this, and these groups are very much favorite for the persons, for the faculties who are taking interviews for this competitive exams. So you take special care about this. For example, for group, consider say R. Is it R and R cross R? Are these two groups isomorphic? Or say Z and Z cross Z? Are this group isomorphic? Or say Q and Q cross Q? Or Z cross Z and Z cross Z cross Z? Are they isomorphic? So these groups, these families of groups, they also very favorite for, they are also very much favorite for the interviewers, those who are taking interviews. So these questions, if you follow it properly, then you will get some extra advantage in during your interview time. So all the questions are these groups isomorphic? Means isomorphic in that sense with respect to this pair, whether they are isomorphic, whether these groups are isomorphic, and so on. So they are very important part of group theoretic part from competitive exams viewpoint. So you must take care of this kind of questions, and they are very much important. So here Z Q cross Z or even Q cross Q. So they are also very important. Okay. So this kind of questions are very much asked in many of the competitive exams. So for that you have to know in detail the properties of homomorphism. So group homomorphism and ring homomorphism, right? And also field homomorphism and also vector space. And in fact you will be reading another course in your next semester, that is module. Okay. So module is nothing but a generalization of vector space. So you know in a vector space you have basically an ordered pair, like V is a non-empty, is a additive abelian group, and then there is a field, say F star, say composition, say this is a field, then this field acts over V, and that action with respect to that particular action you get vector space. That means basically already you in your group class you already have about started with reading, or you might have the idea of what is the group action. So here this is nothing but the field action. Now in a general, well, you in your undergraduate level when you started vector spaces, so you just had this is a additive abelian group and this is a vector, this is a field, and if these properties, some few properties are satisfied, then you call V as a vector space over the field F. Okay. And that properties, the properties that usually that satisfies is nothing but the action of this field over the additive abelian group. Now the same thing also happens here in case of module theory, but it's a kind of generalization. So here it's a additive abelian group and the field is acting over this additive abelian group. So instead of field, if you have any ring R, say star dot, and if you have V plus, and if you consider the action of this ring over this vectors over this additive abelian group satisfying few properties, then we call this is a module over the ring R. So as you understand that any field is a ring, as a result you can consider vector space as a general, I mean as a particular case of module. Okay. So in everywhere you will find the concepts of homomorphism. So you can understand that in group you have actually say one binary composition or operation. In ring you have two binary composition, right? In field you have also two binary composition. In case of vector spaces you can understand that this is there are three basically. So the vector space, in vector space or in module, the homomorphism property actually preserves the this compositions properties. Okay. That's why in case of group you have only this property, say X composition. So if F is a homomorphism, if I write like if a group homomorphism, if F is a homomorphism from G to say G dash, then we are only interested in only this X composed Y should be equal to Fx and Fy, but this say this is respect to say composition dash, then this will be composition dash. Okay. So since there is only one operation here, only one binary operation here, so we are only interested in preserving this binary of compositions. But in case of ring, if F is a ring homomorphism from say R plus dot to say R dash, plus dash and dot dash, then we need to check two properties. Plus y, it should be fx plus dash fy, and another is with respect to this composition. X composition y should be fx composition dash fy, and everything, it has to be for all x y belongs to R. It's not for a particular xy, it should hold for all xy. Similarly, in case of a vector space, you had already the linear transformation and all kind of things. So if you think in a bigger perspective, then you can understand that this linear transformation is nothing but a kind of homomorphism, preserving these properties of plus, star, dot, etc. So that's why if you understand the group homomorphism properly, then the basic idea for understanding the linear transformation, or in case of a module homomorphism or field homomorphism or ring homomorphism, are basically done in a nice way. So when we talk about homomorphism in case of a group, say G to G dash, we must have the concept of kernel of F. So what is kernel of F? All such elements X belongs to G, which maps actually to the identity element of the other group. So E dash is the identity element of the other group G dash. Okay. So all such elements, and in group theory course, in your undergraduate course, you know that this is nothing but a subset of G. So this is a non-empty subset of G, because you know that always goes to E dash. That means E always belongs to kernel of F. Moreover, you can prove that G is a subgroup of G. So first thing you prove that, sorry, ker F is a kernel F is a subgroup of G. Not only that, you prove something else, I mean something more. ker F is a normal subgroup. So you have already had the idea of normal subgroup, so normal subgroup of G. So that's why you can make G quotient kernel of F, because this is a normal subgroup. So this is very important, and you might have heard about the term first isomorphism theorem, and there you might have seen this kind of concept G quotient ker F. So the first question that comes to your mind, that why you can make it a quotient, because unless, in my last class I have already mentioned, unless ker F is a normal subgroup of G, you cannot make it a quotient to have a group structure. Since it has a group structure, it has to be a normal subgroup, and in this result you can see that kernel F is nothing but a normal subgroup of G. Similarly, in case of ring, so in case of ring, as I mentioned in my last class, that the idea of normal subgroup, the similar idea here is the idea of ideal. Okay. So this is nothing but the corresponding idea of normal subgroup in case of group, and in case of ring, this is ideal. So here also you can prove that kernel of F. So if F is a ring homomorphism from a ring R to R dashed, then kernel of F must be an ideal of R. So ker F is an ideal of R. So that's very easy. Now you can prove it quite easily. So you can say that if R is a ring, then ker F must be an ideal of R. So that's not very difficult. You can prove it. How to prove that? The proof is very easy. Suppose you take two elements. So first thing you need to prove that ker F is non-empty. So as I mentioned, as 0 belongs to R and F of 0, since this is a homomorphism, it preserves the identity property. Okay. So that's why by definition 0 element belongs to ker of F. That implies ker of F is non-empty. Now I need to show that this is an ideal of R. So what we need to check? Take two elements, say A and B belongs to ker F. Okay, see, mind that this is a ring homomorphism. Okay, that you need to keep in your mind, ring homomorphism. Okay, then that implies f of a equal to 0 dash, f of b equal to 0 dash. What you need to check, need to show that a minus b is also belongs to Karef. So need to show a minus b belongs to kernel of F. So let's check what is a minus b. So f of a minus b equal to, by definition of ring homomorphism, this is nothing but fa minus fb, but we have already seen that the value of fa is nothing but 0 dash minus 0 dash, which is 0 dash. That implies a minus b belongs to kernel of F, because that is the definition of kernel. So all such elements which maps into the zero element, so take all those elements which maps into the zero element of the other ring, that is R dashed. So a minus b belongs to Karef. Now the first property is done. Then what we need to take, let any element, say let R belongs to R. Then what we need to show, we need to show R A and AR belongs to kernel of F. Okay. Now start with f of R A. By the definition of homomorphism, you can write it FR into FA. Now keep FR fixed, and what is the value of FR? Where A belongs to, so A belongs to Karef, that's why FA is nothing but A dash 0 dash, so this is 0 dash, and that becomes 0 dash. That implies RA belongs to Karef. Similarly, AR belongs to Karef. So altogether, you can say, satisfying all these properties 1, 2, and 3, you can say that Karef is an ideal of R. So we are done. Okay. So that's this few properties of homomorphism, and this kernel F, for group homomorphism, this kernel F plays an important role. When we are actually checking whether two groups are similar or not, then we need to basically check the Karef. If both the groups are similar, then this kernel, the car F plays an important role there. So I'm not giving you the details. I think you might have done all those things in your group class. Okay. So let me try to find few things. Okay, let us define a function f. I think up to this it's clear to all of you. Let us define a function, say from this. So now you know the definition of z quotient 3z. So the elements of z quotient 3z looks like this. So all such elements of this from a plus 3z says that a belongs to z. I think someone joined. No, okay. A belongs to Z, right? So it's basically consists of three elements like 0 plus 3Z, 1 plus 3Z, 4 plus 3, 2 plus 0 plus 3Z. So it consists of three elements, 0 plus 3Z, 1 plus 3Z, and then 2 plus 3Z. Okay. So let us define something. I'm writing it as notation F. Say here to Z6. Now you know, all know this Z6 consists of 6 elements, Z6. So elements looks like 0, 1, 2, 5, right? So 6 elements. You know what is the spelling of this class. By f of an element looks like a plus 3z, 3z, it goes to 0, 1, 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119 3 of A, this class, for all A plus 3Z belongs to Z plus 3Z. Okay, so I have defined something. Now tell me, one, is F group homomorphism? Question 2, is F a ring homomorphism? Question 3, if so, what is the kernel of F? Quickly, first try to give this answer. Is it a group homomorphism? Somebody? Somebody tell me, is it a group homomorphism?
Yes, it's a
Yes,
group
sir, it
homomorphism.
is.
Okay, so your answer, I am writing your answer. It's right, right? Okay, I'm making it right. Is it a ring homomorphism?
Yes, sir.
Okay, it's a ring homomorphism as well. What is the kernel of F?
Elements like 2 plus 3Z.
Elements like 2 plus 3Z. So you are telling elements like, so 2 plus 3Z. Does that, I mean, this is the kernel, right? Anything else? Anybody?
Sir, 0 also with here.
Okay. 0 also be there. 3Z. And then that's all.
Yes, sir.
Okay. Now you will find the whatever you have told me,
Actually, this is
how
সবগুলোই তো
wrong are
কার্নেল।
they?
actually this is
প্রত্যেকটা এলিমেন্ট কার্নেলে থাকে।
How wrong are they?
actually
So you are telling every
actually
element will
this
be
is
okay.
not
Just a minute. Okay, he added few things like every
actually
element
this is
should be
not
within
defined.
this kernel. That means okay, but you told first time for the first glance you told me that this is a group homomorphism, right? And somebody added this. Okay, now I will show you how wrongly you answered all the questions. As I mentioned, I have written something, maybe a symbol, if you remember. So I have writing F like this and I have defined it like this. So first, it's a homomorphism means it has to be a function, right? First, try to check whether it's really a function or not. You will find that it actually does not satisfy the basic property of a function. It's not even well defined. So what does it mean? Well defined means I'm writing it again here. So if you see this, so it's basically the function. It's basically the function. Okay, the function f. Okay, make it red maybe because you did a wrong answer at a first glance. So it was a function from z quotient 3z. I mean, it's not a function. It's a I mean notation from z6 defined by f of a plus 3z equal to pre-A class. Okay, for all a plus 3z belongs to z quotient 3z, right? Now first have a look at this, whether this is well defined or not. Somebody may come with the definition of a well definedness. What does it mean?
Actually, a particular has a unique element has a unique image.
Okay, but how to show this mathematically?
Sir, if A equals to B, then FA must be
What
Converse
equals
is
to
of
F.
one, just converse process of 1 1. A equal to B implies F A equal to A.
So that means you need to check if A equal to B, that should imply FA should be equal to FB, right? Now see 0 plus 3Z equal to 3 plus 3Z. Is it clear to all of you? Because we know that A plus say H equal to B plus H. If and only if in my last class I have already mentioned A minus B belongs to H. So see that A minus B means 0 minus 3, that is minus 3 belongs to 3Z, because that's a minus 3 is a multiple of 3, so they are equal. But does it imply if 0 plus 3Z equal to f of 3 plus 3Z? Because what is 0 plus according to this definition? This should be, this value should be 3 into 0, and this value should be 3 into 3, and where? In Z6. Now this value becomes class 0 and this value becomes class 3. So they are not actually equal. So this actually does not imply they are equal. As a result, this function, that implies f is not well defined. That means f is not even a function. F is not a function. But what you did, you have already proved that F is a group homomorphism, F is a homomorphism, and few of you have already tried to make that kernel F the whole 3Z. That means the building block on which you are making it your theories, that is actually wrong. But you did it your big buildings on a very, I mean, fragile or very weak structure. So it is not even a function, but you have proved that this is a group homomorphism, ring homomorphism, and so. So why I am giving this example? Because while you appear for the competitive exam, so during the competitive exam at your exam hall, sometimes you believe that you did a correct answer. You know that you did a lot of good things. You made many of the you attempted many of the questions correctly, but at the end of the exam, just when you go out of the exam hall or when you just submitted your answer script, you find that some few mistakes you found that you did it very wrongly, but that were silly mistakes. And then when you started talking with your friends, you find that many more mistakes came up. So this kind of things happens because you need to be little more careful while dealing with maybe very easy question. It was like a very easy question to see, but you can understand that this is basically a kind of trap. And in the exam hall, you will find several traps of this kind. So you have to be very careful, and only practice and doing problems may give you the confidence that you can overcome or you can dodge this kind of traps. So you have to be very careful, and you should not be very enthusiastic while looking at a very simple question, because most of the simple looking questions may be troublesome. So you just think a bit, take some time and try to understand the question and then answer. It's not like on every questions you think in a very difficult way. That's not the way, but you should be not very casual on a very simple question. So you should give some respect on each and every question and take a minimum time and then try to give your answer. So that's a one of the very interesting examples that usually I share with my students, because in every classes I have seen that most of the students, they are they get into this trap, and that's why I wrote it in a red color. Okay, anyway, so that's a interesting part of it. So homomorphisms plays an important role. For example, so when we start with homomorphism, then few more terms come into picture. For example, epimorphism, then say monomorphism, And lastly, isomorphism. So epimorphism means it's a homomorphism plus onto. That means surjective. It means homomorphism plus injective. And this is homomorphism plus bijection, means both. So what does isomorphism means? So as I mentioned in my last class that algebraically few of the things looks different. But if you get into the algebraic structure of both the things, you may find them alike. For example, you know all know this K4 and you all know this group Z2 cross Z2. Okay, so both of them finite, both of them are commutative. So can you tell me what are the algebraic properties that you find them similar? Okay, first tell me what are the algebraic properties that you one by one say. First of all, both of them are group, both are groups. Okay, what are the similar properties, algebraic properties that you think? Groups of
Sir, every non
order 4. Okay, sorry, can you
sir
repeat?
every non-identity element is of order 2.
Very good. So every non-identity element of both the groups are of order 2. Very good. Anything else?
Both groups are abelian.
Both groups are abelian. Very good. Anything else?
Both have two generators.
Both the groups have two generators. Can you tell me what are the generators for K4? So assuming that it's EABC,
We can take
and you know
any
what does
two.
it mean EABC?
We can take
Any
any pair of elements between the three objects A, B, or C.
okay. So any pair of two, I am taking say AB. So I'm sure that you all know what is the interpretation and what is the table for Kali table for this K4. So with respect to that, take any pair of elements. So this order of A equal to 2, order of B equal to 2, and similarly in Z2 cross Z2, what could be the orders? I mean generators
1, 0,
of
and
Z2
1.
cross Z2.
100.
So 1 0 and 0 1. So they are all classes. I'm not writing in bracket. Okay. So they are two generators. Good. Anything else? Any
Actually,
algebraic
these
structure they are
generators have
similar?
alike behavior. That's why the homomorphism exists between any two groups. Wherever you will see the homomorphisms, we will just pick up those generators and we'll look at those things which they are behaving alike or not. If they are behaving alike, then we can say there must exist a homomorphism. If not, there definitely does not.
Okay. Fine. Okay. Any other property that you would like to share?
Both groups have the same.
Both?
Both are non-cyclic.
Sorry, I couldn't. Okay. Both are non-cyclic. That actually follows from here. Two generators. Both are non-cyclic. Okay. Then
And
how
have the
many
same order.
subgroups are there and have the
Order.
same? Couldn't get the last word.
Same order.
Yeah, same order I have already mentioned. Both of them are of order 4. So now if you look at the number of subgroups of this, how many subgroups are there here? How many subgroups are there for K4? Now the question is, okay, how
Three
many
non-trivial.
how many subgroups are there for K4? How many subgroups are there of
There are
K4?
total five groups. Identity, the full group, and then we can take E comma A, E comma B, and E comma C.
Okay, so five altogether. Similarly, how many subgroups are there for Z2 cross Z2? The same thing, right? So five. So you can see that there are plenty of algebraic properties. Whatever property that you think of with respect to this algebra, you find that both the groups they share the similar property. So that gives a kind of interesting property, and that mathematically or analytically you can describe this as a group homomorphism. Sorry, group isomorphism. So what does it mean? That means there must be a bijective homomorphism from K4 to Z2 cross Z2 and vice versa. So you can also have a bijective homomorphism from here to here. That's why they are good, I mean, homomorphism, I mean, isomorphism. Okay, now tell me, say I'm writing from the ring. Now I'm considering about ring homomorphism. 2z plus dot defined by fx equal to say 160x for all x belongs to z. Is it a ring homomorphism? What is will be your answer?
Sir, are homomorphisms
No.
required to be unitial?
Sorry,
Are homomorphisms required to be unitial, carrying one to one?
means no, not necessary. So if we
Then,
require, we'll put extra condition.
okay, sir. But still, it is not a ring homomorphism because Z is an integral domain, and in integral domains,
This will
one
not.
must have.
Yes. So this is not a ring homomorphism because you can check it not with respect to, I mean, you can always check it with respect to integral domain, but simply you can check it. So it's basically by definition 160xy, and then you cannot write it in terms of 160x into 160y, right? In general, it's a broadly speaking. So when you are going to show that this is not, you should not make it in terms of arbitrary xy. For example, if my x equal to 0 and y equal to 0, then you can see that this property is satisfied, right? Fxy equal to fx into fy, because all the things are 0. So when you are going to, it's very important. Sometimes the students they make a mistake. When I say something not to prove, then they put it like an arbitrary xy. So if you put x equal to 0 and y equal to 0, then you see that this relation is satisfied actually. If xy equal to fx into fy, but that does not mean that f is homomorphism, because it should be for every x and y. So it's better to put something else. For example, f of 2 into 3, it's not equal to f2 into f3, and that implies f is not a ring homomorphism, right? But if I ask you this question, is f a group homomorphism?
Yes.
So it's a group homomorphism. So we know that all group homomorphism, you know that all group homomorphism from Z to Z, how they look like. All homomorphism from all group homomorphism. That's very important. Group homomorphism from Z to Z. How they look like. Any idea? There is a particular
Fx equal
form
to
of it.
nx type.
It is characterized by scalar multiplication.
Yes. So fx equal to nx, where n belongs to z and nx, both x belongs to z. So if we consider, so you understand that they form a group homomorphism. That part is very easy. But the converse part, I am saying that all group homomorphism should look like this. Now the converse part is little bit tricky, where you need to prove that if you take any homomorphism from Z to Z, then that should look like this, where n belongs to the scalar. I mean that's Z. Okay. So that I think in your group class you might have done this. If not done, then you should do this, because this kind of questions sometimes are very preliminary questions for interviews. So it requires a little trick. So the minimum property and all, but you should read those things. Unless you study all those things, you won't be able to reproduce it maybe in your interview time. So that's quite a formal way of writing. That is very good to know all those things. But unfortunately, if if I ask you the question is consider fx equal to nx, where x and n belongs to z, then f can never be a ring homomorphism. Is your what would be your, is it true or false?
So it is
It
true
must be
Sir,
a
only.
if n is 0 or 1, then it can be true.
Yes. So if this is 0 or 1, then it is true. But if it is not 0 or 1, even in case of -1, then also it's not possible. That means if fx goes to -x, then also that is not possible for ring homomorphism. Mind that. For fx equal to -x, it's a group homomorphism. Can you tell me what would be the isomorphisms from Z to Z? What are the all isomorphisms from Z to Z group with respect to group?
Sir, fx goes to nx.
Fx
Fx
equal to
goes to
x.
nx. Okay, somebody says fx goes to nx, and where n belongs to, if n becomes 0, then what will happen? Will that be a group isomorphism?
Sir, in non-zero. In
Okay,
non-zero.
now your first installment is f non-zero. Very good. Then if it is fx equal to say 3x, will this be bijective mapping from Z to Z?
So subjectivity will fail.
Yes, the surjectivity won't be able to get the surjectivity, right? So it geometrically, or I mean not geometrically, pictorially, you can see that this Z goes to 3Z, right? So all the Z actually goes into this 3Z. Then what will happen for other elements, like which are not multiple of 3? Then how will you get back here? You won't be able to get the surjective mapping. So if you consider any non-zero n, then your that n may not work. So what would be now your answer? What would be your answer? Now I asked you the question, what are all the bi I mean isomorphisms from Z onto Z? Now what would be your answer?
So the
Sir,
identity map.
sir, in
So
must be
it's
equals to 1 or -1.
yes. So it's group isomorphism. Mind
Sir,
that.
sir, uh, actually, sir, I took the question different in a different way. That's why
Okay.
I gave that answer.
Okay. Anyway, so maybe it's my mistake, but anyway. So now you understand what was my question, right? So
Yes, sir.
it has to be either fx equal to x or fx equal to -x for all x belongs to z. If you take any of them, then you will find this thing. And there is a term called automorphism. Have you heard about the term automorphism? That means it's nothing but auto means same or self. So say it's from a same group to same group. Okay. If you have, if you take the isomorphisms from the same group to same group, we call it as automorphism. And the collection of all automorphism, in case of group, we denote it by AUT, aught of G. This is nothing but F is a mapping from G to G such that F is an isomorphism. Of course, it's a group isomorphism. Now, if I ask you the question, what is then automorphism of, it can be proved that automorphism of G is it has a group structure. Okay. So, can you tell me what would be how the automorphism of Z in respect to group? Okay. This should be isomorphic to what?
Z2.
Auto Exactly. It's isomorphic to Z2 because it's a only two elements are there. One is fx equal to x, another one is fx equal to minus x, right? As a result, it's, as I mentioned, automorphism G has a group structure, so it must be a group with two elements, and as a result, we know that every group with two elements must be cyclic. As a result, it must be isomorphic to Z2. Now, if I just change the same question, automorphism of the ring, automorphism of the ring Z. So this is now the ring. What will this look like?
So the
That
trivial
must be
group.
isomorphic.
Only identity.
Trivial.
This is the trivial, only the E. So I can say that 0 because automorphism of with respect to ring, so that has to be automorphism with respect to group as well. So in case of group, we had only two options. We don't need to check any further. Only two options, out of which, in case of a ring, this will not work. So only one element will be there for ring. As a result, it will be only one element. So is it clear to all of you? Okay. Now let us try to check some. So I'm going to develop. So I am going to give you some arguments, and that may be mathematically wrong, but I will pose it in a very smart way. So your idea will be to negate me. Okay. If you fail to negate me, then that will be the proof. And if you have any doubt or any queries, maybe we can discuss it in the next class. Or if we need to impose any such property, then you need to tell me. Okay, it would be a kind of game. So I'm going to give you a small example or a small derivation, and you need to find few of the wrong steps that I made. And if you don't find that, then you have to believe that whatever I did is correct. If you find some mistakes, some logical mistakes, then you need to tell me. Then I may put some extra condition over that to make the proof ready. Okay. So the idea is I'm trying to find the ring homomorphism from R to R. So R to R, real R. So F is a ring homomorphism. Okay. So what are the properties that we know about R? What are the properties that you can tell me? Few properties, algebraic properties are about R. So this is a ring. What extra that you can tell? So this
So
is
I
it's a
will
also a
field.
count.
field. So it's a field. Okay. So it's a field as well. And it's a ring homomorphism. So you can think of this is also a field homomorphism, because if it's a ring homomorphism, then suddenly it would be a field homomorphism. So it's a field homomorphism as well. So I want to find all field or ring homomorphism from the field R to R. That is my aim. Okay. So, my aim is to question find all ring morphisms from R to R? So that's my question. And we are trying to f of 1 goes here. So f of 1. So R plus dot must have an identity element. So f of 1 must be of this form, f1 into f1. And since this is a ring homomorphism, we can write it like this of 1. Now, since this is a field, it must have the property that it must be an integral domain. That implies f of 1, if I make it a common, then I have 1 minus f1 must be equal to 0. And as I mentioned, it's an integral domain. So either I have two choices, either f1 equal to 0 or f1 must be equal to 1, since this is an integral domain. Okay, till now we are within this algebra, and we have seen that there are two possibilities, either f1 will go to 0 or f1 go to 1 if it's a ring homomorphism. So up to this, any ambiguity or any questions? Any loopholes that you found? That means I started with any ring homomorphism, and I found that the identity element, the multiplicative identity element, either goes to 0 or it goes to 1. Now you can understand that the basic property that till now I have used are basically that R is a field, that means it is an integral domain. Now the step that I did till now, can we replace f by any field? Yes or no? So my first question till now, can we replace R by any other field? What will be your answer?
Yes, sir.
Yes.
Yes, we can.
Okay, so your answer is yes, green. Yeah. So till now, nothing special about R. It may be any field that will be sufficient. Maybe infinite or finite, doesn't matter to us. Okay. Let's again go back to our proof. Now, if so, we had two choices. If f1 equal to 0, then what would be your conclusion? Then what would be your
So
conclusion?
so then F maps all non-zero elements to 0.
Okay, and
It
what about
maps
zero
all the
element?
rationals to 0. Conclusion
Has
is F maps
0.
all the rationals to 0.
F maps of all,
Rationals to 0.
and what's about irrational?
Irrational, not I can't tell from this f1 equal to 0. I don't think for irrational I can tell this.
So
Okay,
we have ring structure, so we can split it up.
yes, so let x belongs to any real number, right? Then f of
So
x
then X.
equal to f of x into 1, right? So you can write it fx into f1. Sorry, this is 1.
Okay.
So that means fx into 0, that is 0, for all x belongs to R, right? So what is your conclusion then? So if fx, sorry, f1 equal to 0, then fx equal to 0 for all x belongs to R. Till now, any ambiguity? Any question? Any confusion that I made something wrong or I misled you? You have to be very careful in all my steps. I will do something. Again, if I ask you the same question, till now, can I replace R by any field? Will that be fine? What will
Yes,
be your
sir.
answer? Yes. So,
Yes.
so till now, any finite, any field, not necessarily finite, will be fine with me. Okay. Now, so there is another case. If f1 equal to 1. See, I started with any arbitrary homomorphism from R to R that has to be ring homomorphism, and I have seen that first observation was it can send 1 into only two places, either 0 or 1. So if it sends to 0, then basically it has to be a zero morphism, because fx equal to 0, it's nothing but a zero morphism, everything goes to 0. So it's a homomorphism. So we get already one homomorphism from here to there. Now the question is, are there any other homomorphism? Now there is another choice, that f1 equal to 1. Now tell me what could be the consequence. Okay, so I break my whole argument into several steps. First I make it, say, let n be a natural number. Since this is a homomorphism, 0 will always map to 0. That's fine. Now take all positive natural numbers. That means positive integers. Then what's about fn? So you can add 1 n times. So that means f1 plus 1 plus 1 n times. And that gives you the idea of n of f1. And since f1 is 1, so that means n for all n belongs to natural number. Okay. Now let's n is a negative integer. Let n less than 0 belongs to z. So it's a negative integer. Then what about f of n? So f of n we can write like this: f of uh, minus n into minus 1. Now from ring structure we have f of minus 1. Now as you know that what is the value of f of minus 1, you know that that is minus of f of 1, and this value is minus of 1, right? So that's the basic property of homomorphism. You all have done this. But minus of n must be a positive integer, right? N is negative integer, so minus of n is a positive integer. So just now we have done it for positive integer. If this is a positive integer n, then that value is nothing but n. That means it should be minus n, because minus n is a positive integer. And just now I have mentioned with the basic properties of f, this is nothing but minus of 1, that is n. For all n less than 0 belongs to z for negative integers. So with these two, what will be our conclusion? Our conclusion will be f of n, because in case of 0, we, due to the homomorphism property, f of 0 always go to 0. That's why for negative, 0 and positive we are done. That means f of n for all n belongs to the integer z. Fine. Now we need to check what's about the rational number. So up to this, any ambiguity? Can we do it for any field now? Can we do it for any field now? What is your conclusion?
Sir, for characteristic 0, this is true.
Okay.
And for characteristic, say P, then we can so give us even the argument for ZP inside that field.
Okay, but what is the characteristic of this field? If 2 to the power n, say n is greater than, say, for make it possible, 2 to the power 4. What is the characteristic of this field? If 2 to the
So
power
2.
4, 2. Okay, then you may not be sufficient to consider only Z2, right? So you have to check from F2 to the power 4 to F2 to the power 4. So in that case, only Z2 may not be sufficient. Okay, but that will come to later on. So is it clear? I mean, is the answer clear to your answer? Okay, anyway, so all the steps you need to, he has given a nice try. So the question is, till now, whatever we did, can we do it? Can we do the same or similar steps for arbitrary ring? Okay, if not, then what kind of ring? Can we impose some extra condition? What kind of ring? If not, then on what kind of ring? Okay, so that's again you need to think. Okay, again we come back to R. So in case of R, we are only done with integers. Now there are many other things are left. For example, rational numbers are still left. So let's think about a rational number. Let P by Q belongs to Q, and assuming for the sake of simplicity, assume that GCD of PQ equal to 1. In my last class, I mentioned something about this uniqueness and all. So let P by Q belongs to Q, and without loss of generality, we assume that they are in a reduced form. That means GCD of PQ equal to 1. Now my target is to show f of P by Q equal to P by Q for all P by Q belongs to Q. Can somebody help me in proving this out? How to proceed?
Sir,
Yes.
sir, f of p equals to p,
F of P equal to P. Very good.
and then I can split p into q number of terms
Okay.
by
So
p by q plus p by q times.
Q by Q plus P by Q, Q times. Very good.
And from homomorphism property, we can say that f p by q equals to p by q.
No, not directly. Just tell me a few steps. You are correct. Then what should be this?
Sir, on the right side, that should be p instead of q.
Right side is
P.
F of P, right?
Yes.
F of P. Yes. Then
Then q times f of p by q equals to f of p equals to p.
Q times F of F 1 by
F
what
p
is
by
the
q. F p
F
by q
P by Q
equals to f
equal
of
to
p.
F of P, and this F of P is P.
Yes.
That implies F of P by Q equal to P by Q. Very good. So we are done. Okay. Again, the same question, can we do it for any arbitrary field? And then if so, then what could be the corresponding steps? The same question. Or even can we really do it or not? Or if we impose some condition, can we make it or not? Till now, any question or ambiguity, anybody? Any question? Okay. If not, then what's left? So the Z part, the Q part, we are done. Now we are left with only the irrational part. So let say A be an irrational number, say real minus Q, to show f of A equal to A, right? Okay. So now we are going to real analysis. So you all the results that I'm going to state, you must have done all those things in your undergraduate level. Okay. So how to proceed then? So the thing that the power that we have already at our hand is basically that we have proved the result for rational till rational. So that we need to use, and you know already, all of you must know that there is a relation between rational irrational numbers in terms of some sequence. So for example, if A is an irrational number, then you must know that there exist two sequence. I mean, there are infinitely many sequence, but you suddenly find two distinct sequence, say an sequence of rational numbers and bn sequence of rational numbers. So they belong to, I mean, the sequence, all the elements. In that way, I must write all the elements must belongs to Q. That means two sequence from the entities from the rational numbers, such that an less than a less than bn, and both of them limit n tends to infinity an equal to limit n tends to infinity bn must be equal to a. Is the statement right or wrong? Tell me. What I am saying, if you take any irrational number, then there must exist at least two sequence of rational numbers an and bn such that this property is satisfied, and if you take the limits, then this limit, both of them, they converges to a. Is the statement true or false? So my question is the statement
Yes, sir, this is true.
true or false? What property exactly? So answer, somebody tell me that the answer is true. Okay. So what property did you use to get this? What property? What property of R you used you used to answer yes or true? Key property. What property you have used here?
Sir, the rationals are dense inside the reals.
Okay. So your answer is Q is dense in R, right? So if I ask you another question, is R minus Q is dense in R?
Yes.
True or false?
Yes, sir,
True.
true.
True. So can you prove this? So this kind of questions actually are asked in the interview. While you are using some of the statements, then certainly it may be asked. See, you might have given a option that I am good in algebra, so please ask me questions from algebra. So I started with algebra with a very simple homomorphism things, and suddenly I come into limit and continuity. Not yet continuity, limit, sequence, etc. So now you can understand that I am very much within real analysis because I am considering the dense property of Q in R. Now, a quite similar question is the complement of Q in R, whether that is also dense or not. Then I have every right to ask you the proof of this, right? So that's the way that usually people they face the questions in interview. So as I mentioned, to crack any institutional interview in a master degree level or even in a PhD level, you might have some conservation, or you may like a particular topic. Say for example, if I say in a broad way, you may like algebra, but to crack the interview, you also must know few of the basic things from analysis or topology. Similarly, if you are fond of analysis or topology, I will show you how to convert the questions from topology, analysis, functional, or even complex into algebra. I will show you these questions maybe in subsequent classes. That you may start with your topic that you like, but suddenly through some questions, I will certainly make you put you in a different subject that you may or may not like. That's why for cracking this kind of examinations, you have to be good in one particular subject. If you are good in all the subjects, then that's very good. If not, at least you should have some basic ideas, and they are the basic transforming questions. So in this course, I will basically try to show you few of the this transforming courses through which one subject may be switched into another subject. So that's very important, and many of the students, then they are very good in algebra, then after asking few questions from algebra, then if something is switched into some other subject, they get nervous and they started fumbling and all that. So that is not expected for any institutional, for example ISI or TIFR, or in TIFR nowadays it's only written, but in case of NBHM exam and all, where you will face some of the interviews, then you have to be good in at least two of the subjects. That's my main aim. If you are good in all the subjects, then that's the best thing, but if not, then the bare minimum could be you should have at least two subject knowledge in a proper way. Okay, but you might have some extra lichens on a particular subject, but it's the normal way. We start with some question and then we try to shift you from one domain to another. So that's very important. Okay, so now we are actually trying to use the concepts of real analysis. Let's again come back to our analysis class, I mean our algebra class, sorry. So these properties we all know, and that properties are due to basically the denseness of Q and in R, so on. Okay, so what are the things? So we started with an arbitrary homomorphism which actually sends 1 to 1, right? That was our initial assumption. Two cases were there. Zero case we have already done. Now the case that we are dealing with is basically 1 which is being sent to 1. Okay. Now, first we will show that if we have this function, if it satisfies this property, then f is a monotone function. Monotone function. So what does it mean? Now, to prove this, f is a monotone function, let a and b belongs to R such that a is greater than b. Okay. Now I want to prove that to show what our aim is to show fa is greater than equal to fb. That is our aim. Okay, how to prove that? Since a greater than b, let okay, since a greater than b, a minus b must be greater than 0. Then, so this is a positive real number. Then there exists a real number c such that c square equal to a minus b. Is this statement true or false? Tell me. Or any extra condition I need to impose, or this statement is true? So my question is this true or false?
Yes, sir. A minus b is a positive real number, and we can take square roots of positive reals to obtain that number c.
Okay, so we can always take, but whether that positive, that square root exists, so that's the point. So can you prove this result? Yes, the statement is very well correct, but there is a proof, and well, you are going to prove this, you will find that some infimum, depending on the situation how you are dealing with, sometimes you may prove it with respect to infimum, and sometimes you may prove it with respect to supremum. That depends on how you are taking the set. But this question, if you are doing this step, then sometimes you may be asked that can you prove this result. So you have to be little bit not only studying the results but also the supporting results that you are using, very much they are asked in the interview. So what I am telling, try to prove this. I'm not doing this, but try to prove this. So this is a correct statement and you can prove this. Okay, now if I take f of a minus b, then this is nothing but f of c square. And since this is a homomorphism, I can write it fc of whole square, right? So suddenly this is greater than equal to 0. That implies, since this is a ring homomorphism, so I must have Fa minus Fb, and that is greater than equal to 0. That implies Fa is greater than equal to Fb. Okay. Till now, any ambiguity, any question? Any step that I did something wrong, or I need to put some.
Can we do it in arbitrary field? Can we do it in arbitrary field? We already assumed in arbitrary depth.
No. We are
Can we
already
do
in
that?
R. No. Till now we are in
Okay.
R. So
Okay.
up to this, any ambiguity or question?
No, up to this not, but in arbitrary field, yes.
Yes. As I mentioned earlier, the same question are also here. Is the result true for, is the result true for arbitrary real, arbitrary field as usual, and if not, then what kind of condition? If yes, then what kind of field, and so on. So you need to think about it.
I think the field, field must be finite dimensional. In finite dimensional, I can state fx plus y equal to fx plus fy, then f be continuous. Now I can prove it.
Now what will
In
happen?
So
infinite dimension,
I have a counter example to his construction. The complex numbers are finite dimension over R, but we have the complex conjugation.
The main problem would be your ordering. See, here you can write it, something is greater than something in the field, right? But in case of complex numbers, how will you write it in that way? And if I can write, uh, we can impose some of the ordering by giving some extra condition. Then you have to see whether that result is satisfied or not. Is it
So
clear?
there's one more.
no,
There's
I
one.
am not saying.
Yes.
Sir, take Q adjoint root 2.
Okay.
This is a finite dimensional Q vector space, and we have
Over
an
Q. Yes.
over Q, and we have a notion of ordering.
Yes.
Yet there is the conjugation root 2 goes to minus root 2,
Yes.
and this does not preserve order.
Yes. So,
The answer
so
might be here that the field must be closed under taking arbitrary square roots.
yes. So that's what extra condition. What extra condition that you must put therein. So, I mean, what I want to mention is that when we read normal theorem, so this is very simple looking theorem, right? In any standard book, you might have seen this kind of things. But while doing those things, you should raise your own question. That's the way you should read. Unless you read the whole thing in that way, you won't be able to crack good exams, because there are many things maybe conjugated or maybe added with a particular very simple looking proofs. So you know, all of you know this result, and if you do it for normal things, and then if you don't think about arbitrary field, then your maturity won't be gained. So that's my request. So while you are reading any simple, any whatever, maybe any simple things, just try to associate with, is it, try to ask questions yourself, then ask the question into your Google thing, then you try to Google it, and you may find a lot of answers or similar looking questions, and you will really get lot of extra information while searching in Google. For example, stack exchange, almost all the exams, competitive exam questions are being asked in stack exchange. You will certainly get all the answers from there. So it's a very good practice. When you are searching for some of the particular questions, then you will find a lot of similar questions that you may not be asked or you may not thought about, but you will get a lot of extra information out of that. Okay. So anyway, so what we proved here is basically F is simply an order preserving. It preserves the order. If A is greater than B, then suddenly you will have an equality, extra equality might be here. Now my question is, can we give some condition, or whatever step that we did, can we also have a strictly greater than? So that means, can we have, we didn't say R, can we have in R, where we are actually doing A greater than B implies FA strictly greater than FB. What I did, I put an equality here with some argument, or with the same argument, can we have a strictly FA is strictly greater than FB? That means exact is a strictly monotone increasing function. So till now what we did is a monotonic function. Can we have the same thing, the same argument, but we have in a strictly monotone increasing sense? That's a question that you may also think. Okay, so till now what we did is basically f is a monotone function, and also we had these properties, dense property. With respect to dense property, we also had take any irrational number, then we had two different sequences of rational numbers satisfying this property. If I take this limit, then it converges to A. Okay. Now we are very close to the end of the proof. Let us have a look at this. So again, so what actually we are left with? We are actually left with this case. Let take any irrational number. Okay. Then we need to show need to show f of A equal to A for all A belongs to R minus Q. Okay, as I mentioned earlier, since A belongs to R minus Q, from the dense property as we've already seen, there exist two sequence of real numbers, two sequence of, sorry, rational numbers, say An and Bn, such that An is strictly less than A, strictly less than Bn, and limit n tends to infinity An equal to limit n tends to infinity Bn equal to A. Okay, mind that these An and Bn, they actually are from rational numbers. That's very important. Okay, then so as An less than A less than Bn, that implies f of An less than equal to f of A less than equal to f of Bn. Why this is so? Why I get this step? Because just now I have proved it's an order preserving, but this equality may come, right? Just now we have already seen. That implies if I take, what is f of n? This is a rational number, this is a rational number. So f of n must be equal to, I must write it, an, because in case of rational number we have seen f of A must be A if A is a rational number. So that is less than equal to fa, that is less than equal to B of n, as f of An equal to An, f of Bn equal to Bn, both belongs to Q. So already we have proved. Now if I take a limit on all the sides, n tends to infinity fa less than equal to limit n tends to infinity Bn, then what would be my result? So just now we have already seen that this limit goes to A. So we can write like this. So this is a less than equal to, so this is fa independent of n. So this must be fa, and this is also less than equal to a. What does it mean? Fa equal to a. Clear? Now tell somebody, is there any kind of mistakes or any kind of steps that I have done is not correct? Any step or any of the places where, tell me, any logical flaw that you found here? Okay, so I'm giving it as an exercise. So try to find some logical flaws here and try to prove it for arbitrary field, and then what extra condition that you impose. So after that, after doing all these steps, what is my conclusion? My conclusion then is, so fx must be equal to x for all x belongs to R, because we have seen that for natural number, positive rational number, zero, negative natural number, then we have seen it for rational number, and now we have seen it for irrational number as well. So here a was my irrational number, that also gives me a. So if you take any real number, then it becomes this. So why this condition came? Because our assumption was f1 equal to 1. So what was your conclusion then? The conclusion is, if f1 equal to 1, then fx must be equal to x. Now, is it clear to all of you? Any question or queries? If you have, please ask me. Please let me know any queries or any questions. Okay, so what we get now, let me ask you a few questions. Okay, question one, automorphism ring, okay, R plus dot, what will be, is isomorphic to what?
So the trivial group.
So the trivial group. So I can write it like, so that means fx equal to x is the only automorphism, right? So this is the trivial group. Okay. If from R to R is a ring homomorphism, then, so f must be a function, then f is continuous. True or false? See, this is an analysis question, but I asked it in very much in a homomorphism question. So is it true or false?
Yes, sir, it is true.
True.
Okay, what other, somebody else was trying to say something? Is it true or false? Okay, let me ask few of you. Uh, let's see. Aniruddha, are you here?
Yes, sir. It is continuous.
Is
Yes,
it
sir.
continuous?
It is continuous.
Okay. Bonusri, can you tell me, is it continuous or not? Bonusri, are you here? Okay, I cannot get your answer. Aja Bhaskar, are you here?
Yes, sir, continuous.
Why? Why continuous? Okay, you need to. Then who else? Kailash,
Yes, sir. I think it is continuous.
why?
Sir, I'm thinking, sir, the logic.
Okay, it's trivial answer. And then Probitro,
Such thing continuous.
why?
The logic I am thinking.
Okay, okay, it's a very trivial. Uh, so you must think and give me the answer. It's really trivial. Anyway, so that means you can see from here that we started with the questions from algebra, but we end up with the questions of real analysis and all. So it's very interesting to see all those kind of applications here. Okay, now I will go, I will show you another very simple. Now, can you find in a different way, can you find, say, you have heard about this, say, complex numbers, and you know that M2R, okay? So, can you find some homomorphism from C to R such that, so suppose this is C and suppose this is R, such that, so this is M2R, M2 real R, such that the C will lie inside, so this is C, will lie inside M2R. Can you define in such a way so that this complex number can be thought of as if the structure of complex number is within M2R. So they are matrices. So algebraically they looks like all 2 by 2 real matrices, and it's a complex number. So apparently they looks very different. But what I am saying, can you embed or can you give some function f such that that complex number, whole complex number can be thought of as it's within M2R? Can somebody try to give me a function? So one complex number looks like this, right? How it should be?
So I'll map it to A, then B, then minus B, then A.
Okay. So he has given a mapping and suddenly this belongs to M2R, right? There is no doubt about that. Now, first question, is it well defined? Can you tell me, is it well defined? Is it well defined? So the question is, when shall we look into this well defined concepts? Is very much well defined. So usually the well defined concepts, if you go little deeper or if you think little deeper, then you will understand that it comes when the confusion comes. So the confusion actually comes when the similar looking things appear more than once. For example, in case of z 3z, 0 plus 3z and 3 plus 3z and 6 plus 3z, they are all same here. As a result, a confusion may come when they are going to some other places. For example, Z6, their representation given by some f may not satisfy the property fa should be equal to fp. But here there is no kind of confusion here, so you don't need to check into the account of whether that is well defined or not. But you need to think more deeply that when we should go for well definedness and when not. Okay. Okay, so but the second question is if a homomorphism, what would be your answer? How to check? You can check that. So of course, homomorphism with respect to what? With respect to ring. You can think that you can think this as a ring, and then M2R may be considered as also as a ring. Then is it a ring homomorphism?
Yes,
So
sir.
first,
It's a ring home under
is it
Addition, it's a ring homomorphism, but not in multiplication.
Okay, so let's check whether the multiplication is also not. With respect to addition, you say that it's a group homomorphism, no doubt. So let us check whether
Not a
it's
ring
a.
homomorphism.
Okay, let's see. You need to check like this. So can you tell me very quickly what is this value? This value is A. What is this value? AC minus BD plus I into AD plus BC, right? Okay. And then it should go into like this: AC minus BD AD plus BC minus of AD plus BC, and here AC minus BD. Okay, so that's the f of AB. Now try to check what is this value: A B minus B A into C D minus D C. Can you multiply it quickly? Tell me what is this value? This
Sir,
is
same as the above.
AC minus BD. Oh, it's giving the same answer. Oh, quite strange. BC. So this is BC minus AD, and this is AD plus BC. This is minus BD plus AC. Oh, it looks same. Then what would be your conclusion? Who told that this is not a group homomorphism, ring homomorphism? Now is it clear to you? So it's a ring homomorphism. So you can see that with respect to this is nothing but f of A plus IB into f of C plus ID. And this is not for any particular ABCD. This is for all A plus IB, and C plus ID belongs to C. Okay. So now you can see that this is a ring homomorphism. Now tell me, is this ring homomorphism injective? So question is F injective? What would be your answer? True or false? What would
Yes,
be?
sir.
Okay. So
Yes,
to
sir.
check whether this is injective or not, there are many ways. You can try with A not equal to B, that implies FA not equal to FB. But if homomorphism is there, then you can also try with CARF and check whether CARF is the identity or not. If your CARF equal to identity element, that means CARF contains only the identity element, then your answer would be F is injective. So which way you want to go? Any way you want, you can proceed in both way. Let us have a look at what is the kernel of F. What is kernel of F? All such A plus IB such that f of IB, f of A plus IB, that must be the zero element here. What is the zero element? 0, 0, 0, 0. Okay. So that means A plus IB such that A B minus B A must be equal to 0, 0, 0, 0. Then what is its implication? A B must be 0, 0. That means 0 plus I0 is the only set. That means the zero element of C. As I mentioned, so this is the identity element. So since CARF is E, so my conclusion is F is injective. So now we have done something. So I have a mapping F which goes from C to M to R, And so f of c is here. Now tell me, so f of whole c, it's a capital C. Now tell me, what is the relation between C and FC? What are the conditions given? F is an injective homomorphism. That means an monomorphism. So what is the relation between C and FC?
So they are
Sir,
isomorphic.
that's not.
So because the mapping, if I consider the mapping from C to FC, then F, in that case, in that restriction part, then from C to FC, from C to FC, F must be onto. It's also given it's injective, also given it's a homomorphism. As a result, altogether it's an isomorphism. So what you algebraically tell that C and FC are isomorphic as rings. As a result, C must be identically same as FC with respect to algebraic operations. As a result, you can think of that M2, within M2, C is lied inside M2R. That means you can consider M2, though algebraically it's a ring of matrices, but still you can think that very well that within that M2R, C is lying inside. So you can see that M2R is not a field, but C is a field. So within that ring, you can have a field which is lying inside, and that is called embedded. So if there is an injective homomorphism from one ring to another, then suddenly the left hand ring is considered to be embedded. That means you can insert algebraically the ring R into the bigger ring R dash. Okay, so that's the idea of ring embedding, and there are plenty of interesting properties with respect to ring embedding. So whatever I did is basically a basic preliminary for ring homomorphisms. So that is quite interesting. So in my video lecture, you can find, when you will open this video lecture, I will give the link of the assignments. So till now, whatever the instruction will be there, so I will send you the instruction. But when I will upload this video in the YouTube, in the comment section, I will also put the link of the assignment. So that assignment you need to upload in a regular basis, not in a whole day. It's a whole ring theory assignments. So you can, I will divide the whole tenure into different parts so that you will have some deadline to submit this assignments. So if you are interested enough, then you can do it in one go, but there will be some deadline when to submit, and I will share the link with all of you who are in the class uh, through some link. But the link for the problems will be for all, so anybody can solve this problem. Okay, so till now, any question? Okay, so if not, then just try to think about what's about the quaternion ring. So you remember the quaternion rings look like A plus IB plus JC plus KD, so that A, B, C, D belongs to R, right? You have already seen this. Can you have some kind of matrices, say M, N, R? So first you need to fix up what would be the value of N. In case of complex number, you can see that only this part was there, only this part was present, this part was not there. You made it N equal to 2 in that case. But here you have all J and K. Then what would be the value of N, so that you can embed this quaternion ring into a suitably chosen N, M, N, R. So that is your homework. Is the question clear? Now what I want to say, that you need to embed the quaternion ring into some suitably chosen matrix ring. So try to find the minimum size n, so that this quaternion ring could be embedded into MNR, where n is the minimal chosen number so that the whole quaternion ring can be embedded inside MNR. For example, in case of complex numbers, you had only a plus ib, and you have embedded a plus ib into m2r. So the value of n was 2. Now I have extended it because, as I mentioned in my earlier classes, that quaternion ring is nothing but an extension of complex numbers. So here you also have j and k. So now you need to choose n properly, and you need to define a function. For example, here we have already defined the function like this. It was the definition of the function. Now you need to consider this element as an element of a quaternion ring, and then from quaternion ring you have to define this matrix, where this n value you need to choose it properly so that it should be the minimum value. Okay, so that's one extra question that I am asking you, so that you need to solve.